Well, now I want to switch over to Dr. John Abatzoglou. John, I'm going to let you, if you don't mind, give a little bit more of your background. But John is a member, a PI of the Climate Impacts Research Consortium, the CIRC. And aside from Phil Mote, he's also our climatologist here. And John's been doing quite a bit of the work looking at how the latest global climate models relate to our region specifically, so here in Oregon, Idaho, and Washington. And John's also a professor at University of Idaho. But maybe, John, you could tell a little bit more about your background?
Sure. So I've been at the University of Idaho for about 4 years, and I'm a weather weenie. I'm a meteorologist, an atmospheric scientist by nature, but I'm also someone who studies the atmosphere across a variety of timescales, looking at both sort of historical climate and then also climate of the future. And in addition to someone who is interested in understanding sort of the nuts and bolts of climate and weather, I'm also interested, and I also study how the atmosphere and the climate system impact things like our water resources, our ecosystems, and agriculture.
Okay.
I think we're good, John. Thanks.
We're good. All right. So what I'd like to do today is to give everybody an overview of climate, and particularly climate modeling, and specifically how we go about trying to understand what future climate is going to look like in the Pacific Northwest, in the Bigwood Basin, and how we can also use this information to help guide our decisions to increase how resilient we are to climate variability and climate change. And we can start off by advancing the slides. What's going on here? Okay. Oh, there we go. It's just lag. Okay. Hopefully things are going to be easier. So I'm a climatologist, and I'm also a geographer, and a lot of geographers look at maps and they see certain things. They see roads, they see where people live. And when I look at maps, specifically maps of the Northwest, I see gradients in temperature and moisture. And these gradients in temperature and moisture help define much of the resources that define the Northwest. They define where we get our water, where we have our forests, where we can grow agriculture, and those things ultimately define our culture and our economics. And we know that in the Western United States, we can drive 5 or 10 miles and we can be in a dramatically different area, and that's primarily driven by the complex topography that we have. And so the idea behind that is that if climate and these patterns of temperature and moisture define our resources, then we might expect that if climate were to change, we also might expect changes in our resources, our economics, and also our culture. And again, like I mentioned, climate by itself usually is not newsworthy. When we get what we expect, if climate is sort of what we expect and weather is what we get, we shouldn't really talk about climate. But oftentimes, climate doesn't necessarily give us what we expected, and we tend to notice climate when we see impacts. We see things like the wildfires across much of Idaho last year. We see things like drought. We see things like too much water at a given time. And also in some of the forested ecosystems, we can see sort of indirect effects of climate through things like bark beetle attack that manifest themselves when we have a combination of drought with a lack of cold mortality during the winter. And these things occur, have occurred through time, and the question is whether or not they may be occurring more in the future, and what we might be able to do to increase our resilience to these impacts. So today I'm not going to talk about global climate change, and the reason for that is that the three words global, climate, and change are sort of abstract if you just look at them individually. And when you throw them together, global climate change, it's sort of this, this term and phrase that is very difficult and abstract to deal with. It's not in my backyard, it's off in the distance, and that often sort of implies that one cannot do that much about global climate change. So instead we'll focus on what's happening at more local scales. And here we're looking at a time series of mean temperature. This is the annual mean temperature for Blaine County in Idaho over the past 118 years. And the blue colors are indicating temperatures below the 1980 to 2010 normals, and the red temperatures are indicating above. And we can see that the warmest year on record is 1934, and that shows up across much of the western United States. But it's pretty clear that if you look at the last 20 or 30 years, that 20 or 30 years is very unlike any other time that we've seen over the period of record. And this sort of mirrors what we see in the Northwest in terms of regional warming trends, and to some degree it also mirrors what we see globally. Now, we might think about temperature as being, one indicator, but oftentimes, there are other things besides temperature that actually might be more important. And these are just a list of a few things that we've seen in terms of additional climate indicators in the Northwest, things like decreases in spring snowpack, and advancement in the timing of snowmelt runoff, increases in stream temperature that are problematic for cold water fisheries, an earlier spring bloom, which doesn't sound like a bad thing, especially now that we are officially in climatological spring. Not sure that the Northwest believes in climatological spring starting in March. We've also seen decreases in the driest years on record in terms of water year runoff. We've seen longer growing seasons, and we've seen a dramatic increase in the coldest temperatures each winter. And the list goes on, but the point is that we do see impacts across a variety of indicators, across a variety of systems. The purpose of the talk here today is to not necessarily talk too much about the past, but instead sort of reconcile whether or not we can understand what might happen in the future, and specifically how we actually go about making these sort of projections of future climate. So unlike classical sciences in chemistry or biology, where one has the luxury of using lab rats, where if you want to test out whether a certain serum is going to have an effect in curing a certain condition, you could take 100 lab rats, inject them with a serum, and you actually do some statistics on that. With Earth science, we don't necessarily have that capability. We have one Earth. We're trying to colonize more planets, but that's not going to happen anytime soon. So what we're left with is the option of trying to best represent the physical properties in the Earth climate system numerically. And we do this using physical principles. So when developing these models of the global climate system called global climate models, we are trying to represent all the physical processes. We're trying to represent the weather. We're trying to represent the oceans, how the oceans communicate with the atmosphere. We're trying to represent the land surface, vegetation, the uptake of carbon through photosynthesis, the ice sheets, etc., and how they interact through time. And these things are based on physical processes. These models are run on some of the world's most powerful supercomputers because they're quite intensive in terms of how many calculations they need to do. And they do a pretty good job. Now, when we talk about models, oftentimes people sort of poo-poo models. They're models, they're not the real world. We'll talk about some of that, and we'll give some sort of credibility to these models. But at the same time, these are models. They're not necessarily going to be answers, but they're going to be tools. And so these tools these tools can help us sort of guide decision making. And you might think about, do you actually use models in your day-to-day life? I think we usually do, and probably the sort of easiest connection between global climate models and the models that we use on a day-to-day basis would be the numerical weather models that are used to develop weather forecasts. Before we had the capability of developing weather forecasts, we suffered far more in terms of the impacts of weather. And these models, these weather forecast models, while they aren't always correct per se, they save an incredible amount of money and lives on a year-to-year basis. So models are models, but models are very useful, and they help us to make better decisions. Now, models aren't always right, and this is something that I think we see. However, what we'd like to also talk about is whether or not we should use all the models available to us. So one way that we can actually develop some credibility in these models before we actually start using them to guide our decision making is to test how well these models actually do in simulating climate for the Northwest. And what actually has been done is there are about 30 different modeling centers around the globe, and they've all developed their own climate models. There's a lot of similarities between these models developed from these different groups. They all have an atmosphere, an ocean, etc., etc. They vary in terms of their spatial resolution. These models typically have a spatial resolution in the atmosphere of on the order of maybe 100 to 200 miles in terms of a distance latitudinally and longitudinally. And they also vary in terms of how they represent things like topography. So you can imagine if you had sort of this, this grid, this sort of modeled world, it would be challenging to represent all of the topographic features that define, in particular, the Northwest. You would have very sort of smooth topography. So before we end up using all of these models and sort of, start making decisions on how we actually might see climate evolve over the next 50 to 100 years, we can look at how they represent climate of today. And this graph here on top, we're looking at the climatology, the average temperature on a monthly basis from January through December, and the black dash or the black solid line is showing our observations. And at least for temperature, we see that these models are capturing the seasonal cycle in temperature, which they ought to be, just on basis of latitude. But they do a fairly decent job with that. The more challenging one would be precipitation. And while the seasonality of precipitation changes as you move from the Pacific coast towards the inland locations, we generally see this Mediterranean type precipitation regime with wet conditions during the cool seasons and dry conditions during the warm seasons. And that's shown in the bottom graph. Again, we're looking at monthly precipitation. And the models in general get the shape of that distribution correct. What you will note, though, however, is that the models tend to predict a little bit more precipitation than we actually observe across the Northwest as a whole. And there are a few models that do some interesting things where they're predicting peak precipitation during the months of, say, June, or even peak precipitation during the months of March. And those might be models that we may consider not using. If they're not able to replicate some of the basic features of climate for the region, then they may not necessarily be able to capture some of the processes behind how that climate is going to change going out into the future. So we go through this screening process, and we look at a number of different variables. We look at temperature and precipitation. We look at how they vary interannually, how they respond to large-scale modes of climate variability like El Nino. And from that, we can reduce our set of models to a smaller set that we think do a reasonable job in simulating climate of the Northwest. This graph here just shows the spatial depiction of that, and we're looking here at observations shown on the left-hand side, models on the right-hand side, and this, again, is over the entire North Pacific Basin. But what you can see to a decent degree is that these models are capturing the spatial patterns as well as the seasonal patterns. So can models actually reproduce observed climate? To first order, yes, they can. And that's a good sort of token in terms of using them as a basis for going forward. Okay. So what I will say before we start to look at these projections of the future is that climate science, like most sciences, is an ongoing process. And in that we know quite a bit about how climate works, how the atmosphere works, how the ocean interacts with the atmosphere. And we're learning more and more as time goes on. In other words, we're adding more and more pieces to this puzzle. And it may be that we never completely solve this puzzle, as we even as we add pieces time through time. But with the issue of global climate change, we're sort of faced with making a decision on how we might be able to adapt or respond. And one option would be to wait until we actually fill this puzzle in completely. And again, that may take some time. The other option is that we can look at this puzzle and we can think we have an idea of what we're actually looking at here. And from that, we can start to make decisions today that may be able to help us down the road. So I will say that these models have been run over the 20th century, and they've been run using a variety of sort of, changes in things like solar variability, volcanic forcing, changes in greenhouse gases. And when we throw in all of the forcings, all of these factors that we've observed change, greenhouse gases, solar variability, volcanic forcing, we find that these models are able to simulate the spatial patterns of changes in climate, changes in temperature, changes in precipitation, changes in wind patterns that we've actually observed. So we think they do a pretty good job in terms of how they respond to the observed changes in forcings. And if we want to predict what's going to happen going out into the future, we have to have some basis through which we can actually run these models. And for future projections of climate, what we end up deciding is that we don't really know when sort of volcanoes are going to erupt into the future. They're fairly stochastic. We've actually seen that solar variability has relatively nominal impact on global temperatures, at least over the past century. And what we've also seen is that changes in greenhouse gases and aerosols seem to be the big lever that has altered long-term changes in climate over the past century. And therefore, when we're trying to think about what's going to happen going out into the future, we actually can use future scenarios of changes in emissions, changes in greenhouse gases. And those things are very uncertain. They depend on populations, in terms of populations, how we use energy, how we share energy, what type of economy globally we have. And socioeconomics have determined a number of different pathways going out from 2000 to 2100 in terms of how the future world might look. And there are several different pathways, and what we'll do is focus on a couple of these here today. And we're going to look at these in terms of the amount of extra energy that is trapped in the Earth atmosphere system by adding greenhouse gases into the atmosphere. And so this graph here is showing the amount of extra energy in terms of watts per meter square between 2000 and 2100. And this blue pathway is a pathway where basically we continue in terms of population, our usage of energy, etc., and we end up increasing atmospheric concentrations of greenhouse gases significantly. By contrast, we'll also focus today on this red pathway, and this red pathway is a pathway in the future where we most likely do start to change the way in which we utilize energy. We still increase the amount of carbon dioxide in the atmosphere, but it's not as acute as the blue pathway. And sometimes these sort of numbers here in terms of radiative forcing are relatively abstract to deal with. So what I find as being useful is to look at where we are today relative to where we were in 1850 before the Industrial Revolution. And the addition of CO2 and methane and other greenhouse gases into the atmosphere have basically added basically added about 1.8 watts per meter square globally. So that's equivalent to putting one of these 100-watt incandescent light bulbs every 20 by 30-foot plot on the face of the Earth. Nominal amount of heating, but it actually does have an impact. And if we think about what's going to happen going out into the future, there's a future where basically we could have up to 5 extra light bulbs every 20 by 30-foot plot on the face of the Earth. That's sort of this blue RCP, representative concentration pathway 8.5. The red pathway, the pathway where we actually do start to reduce our emissions and the way we use energy, might lead us to a 2 light bulb future. So keep those 2 pathways in mind, because we'll sort of focus on those 2 pathways when talking about projections specifically for the Northwest. Now, we're going to be talking about long-term climate projections, and it's important to point out here that when we're talking about climate projections, we're not talking about making forecasts. We're not talking about making weather forecasts. When making weather forecasts, we're trying to say something about the state of the atmosphere at a given point in time. For example, the atmospheric conditions in Ketchum on Sunday at 12 noon. So that's not the purpose of climate modeling. We're not trying to actually forecast what's going to happen on an individual day or even an individual year in the future. And the difference is that when we're doing weather forecasting, we're using sort of the current state of the atmosphere, and we're sort of iterating it forward in time. We're really using sort of that initial conditions and defining what's going to happen. So if we know there's a storm over the Pacific, that's going to be important in terms of whether or not we're going to see moisture in 2 to 3 days. For climate modeling, those things are not as relevant. What becomes relevant are the sort of more slowly responding factors in the climate system, things like greenhouse gas concentrations, sea surface temperatures, and sea ice conditions, and also snow cover conditions. Those things end up being more important. So before we end up showing these projections, we'll just throw out a few caveats on how this information should not be used. And again, these are projections, they're not predictions, so don't ask the model what's going to happen in 30 years on this date, or don't ask the model what's going to happen in the year 2043. That's not a good sort of way of going about things. These models are going to give you better information when you're looking at a longer time period. So it might be more fair to ask what, how the climate might change in the 2040s to the 2050s versus just looking at a single year in the future. Also, we talked about a number of different models, and these models have all been run with the same sort of scenarios. They've all been run, the same experiments have been run on all of these models. And so we have this pretty large set of models to choose from. And if you use a single model, that's like putting all of your eggs in one basket. Or, when we go to the sort of presidential elections, it's like letting one state have all of the electoral votes. So I think it's a better idea to sort of collectively pool the model responses, and that can help get us a better sort of sample and representation of what we might be looking towards. Also, people talk about whether these models are going to be useful for looking at climate and climate variability over the next decade or even 2 decades. And the answer to that is probably not as much. And the reason is that on sort of near-term sort of projections, the variability in the climate system at the regional scale is likely going to trump any sort of long-term climate change signal. So El Niños, La Niñas, for the next 20 or 30 years, they're going to have a much larger signal than the signals coming from pure climate change. And when you get out beyond, say, 2030 or so, then these projections become more relevant. They have more weight. So we'll start here by looking at global projections, and this is the only global projection I'll show you. And on the x-axis here, we're looking at global temperature anomalies from sort of the late 20th century. The gray curve here is showing our observations, and we've seen globally an increase in temperature of about just less than a degree Celsius over the last century and a half. And then if we look beyond 2005, these models have been run from 2006 onward. We see these different sort of pathways, and these pathways are all responding to these different scenarios I mentioned before. So that pathway where we basically have the 5 light bulb future, the RCP 8.5, this is the business as usual. We can see a global increase in average surface temperature of close to 4 degrees Celsius. By contrast, if we look at sort of the future where we do mitigate and reduce sort of our emissions, this is the RCP 4.5 pathway, and it's sort of this cyan or light blue color. The global mean temperature change is about 2 degrees Celsius. So there are some differences, and you can see that those differences are really manifested after mid-century. You also see there's also quite a bit of variability even at the global scale, and again, those things are coming from the different models themselves. Okay, so now that we're going to leave the global scale, we'll go down to the scale of the Western United States. And for the remainder of the discussion here today, we'll focus on mid-21st century, and that's basically taking the years 2031 to 2060, and we'll be comparing these years to the latter half of the 20th century. And when we're comparing these two together, we'll be looking at differences. So the top row here is showing the 28 model average. So we've taken 28 models, we've run them through the same experiment, and now we're looking at differences between these two time periods, and this is the average response. In the annual mean, we see this sort of signal here across the Western United States. We can look at the color bar on the right, and we notice that all of these colors represent increases in temperature. We can see that in general there's a little bit more warming over the interior portion of the Western United States than elsewhere. The oceans do not warm as fast as the land on any sort of time scale, and so that's why we end up seeing a little bit more warming over the land versus sort of coastal areas. If we look across the seasons here, we actually see warming to be largest during the summer months, so at least over much of the northwestern portion of the United States, and that warming is on the order of about 3 degrees Celsius. There's variability in this, and we'll get to that in a bit, but this is just the average response. So that's temperature, and on the bottom row here, we're looking at the precipitation response, and this is future precipitation divided by historical precipitation. So where we see the blue colorations, those are areas where the models are predicting an increase in precipitation. The magnitude of the increase is relatively minor, especially in the annual mean. These are changes that are on the order of about 5%, at least for much of Idaho and much of the northern tier of the western United States. When we look at the seasonal response, so I should have mentioned this earlier, DJF, that's December, January, and February. What we can see is there's actually an increase in precipitation during the winter months. And if we go towards summer months, this is June, July, August, what we can see is actually the opposite, where we see a decrease in precipitation over sort of the northern tier of the western United States during the summer months. So just to show you the sort of spread in these models, just by showing that one graph, that one plot, I'm showing you just the average, but oftentimes when thinking about future scenarios, we might want to consider not only what the mean response is, but maybe we also might want to consider the worst case scenario or the best case scenario. So to do this, we can look at projections of temperature, and we'll do this by looking at temperature for both in terms of temperature change for the annual mean for winter, spring, summer, and fall. And we're also going to look at this for a variety of different climate models and experiments. And so the climate models that I'm talking about here today are part of this new set of models produced for the next Intergovernmental Panel on Climate Change report, and that report is going to be coming out later this year. We'll also look at the previous set of models that was part of the last report that was released in 2007, and we want to just compare whether or not these models are saying the same thing or not. And so the silver and the gold models here are actually responses from the previous set of modeling runs. The blue and the red, these are the newest set of model runs, and the blue represents the 4.5, the red represents the 8.5. So in the annual mean, we can see a lot of information here. For one of these sort of columns, the individual dots represents an individual model response. The sort of box plot shows us the mean and the 95% confidence interval of the mean. And so I'll show you now the results for all of the models, all of the seasons. And what we can see here are a couple things. Not one model is predicting a decrease in temperature. So that's the first thing. The second thing is that these newer set of models are actually predicting slightly more warming by mid-21st century than the previous set of models. And so if you focus here in on spring, March, April, May, what we can see here is that this set of, the red set here, the RCP 8.5, predicts a mean change in spring temperature of about 3 degrees Celsius. You can also see that some of the models are predicting well beyond that. And so some of them way up here, they're predicting above a 5 degree Celsius increase. And on the lower side, there are some models that are predicting an increase of only about 1 degree Celsius. But by and large here, looking at this pool, these models are suggesting an increase of about 3 to 5 degrees Fahrenheit by mid-21st century, and slightly more warming during the summer months, as you can see here in this row. So that's for temperature. When we move to precipitation, we see something quite different. So here's precipitation, and again, annual, winter, spring, summer, and fall, going from left to right. The y-axis here has 0 as the reference point. Values above 0 increases, values below 0 are decreases. In the annual mean, what you see are actually models tending to suggest an increase in precipitation, a very nominal increase in precipitation. We're talking about maybe 5%. And when you look at the sort of seasonal decomposition, what you see is that increase is primarily coming during the winter and spring months. So you see sort of a preponderance of models with an increase, showing an increase in the winter and spring months, whereas in summer the models are tending towards slightly drier conditions, and that might not necessarily be super important from the hydrologic perspective, because summer is not necessarily a month when we necessarily collect a lot in terms of stream flow, but the decrease in precipitation during the summer months might be important for things like wildfire, which tend to occur when we have very low fuel moistures. Okay, so just to put this in some perspective, we'll take a little bit of a local example here, and we'll look at a map that most of you should be familiar with, and we'll consider Ketchum and Ketchum's sort of climatological temperature, mean temperature for the months of March and April today. It's about 34.5 degrees Fahrenheit. Okay, so the question is, if we go off into the 2040s, 2050s, and we see a warming of about 3 degrees Celsius, or about 5 degrees Fahrenheit, that would mean that Ketchum's March and April temperature, the average temperature over those months, would be close to 39.5 degrees Fahrenheit. Where would you have to go today to find an average temperature during March and April of 39.5 degrees Fahrenheit? Where would you have to go to find those temperatures? Any guesses out there?
Somewhere south.
South.
Good idea. South probably is a good idea. So there's probably a lot of places you could go. Here are a few places that I found have current March, April temperatures of about 39.5. So this is Richfield, Pocatello, and Idaho Falls. So for those in Ketchum, you had your temperatures 5 degrees Fahrenheit warmer, you'd sort of, position yourself where current temperatures are in some of these locations. And that can have some pretty important impacts for the local economy in terms of ski resorts and a number of other things besides just ski resorts. And we'll get to that here shortly. But these changes in temperature can actually lead to dramatic changes in climate, especially when we're talking about local scales like this. What we've talked about so far, we've been looking at large-scale climate models, and those scales of these models are very, very coarse. We're talking, again, about 100 to 200 kilometers per pixel, and that's not necessarily going to be the best in terms of drilling down and deriving local scale information that we could actually use in terms of driving a hydrologic model or getting information about what it means for agriculture. So what we actually do is we take these models and we derive statistical relationships between them and historical climate to yield fine-scale spatial patterns through something called downscaling. And this sort of gets us the information that we actually need to make tractable and practical decisions. So I won't describe the details through which we downscale the data. Instead, I'll just show you some of the products that we actually end up producing. We're doing this downscaling for not only temperature and precipitation, but also a lot of the sort of surface meteorological variables that are relevant. So things like solar radiation, wind speed, humidity, and basically what you end up getting is daily fields of weather that are coming from these climate modeling experiments. And this is a map here of 3 different fields of temperature, accumulated precipitation, and downward shortwave flux, which is just solar radiation. And I'll show you this just for 3 days, but what you can end up seeing is you're getting these basically weather patterns that look very much like current weather patterns in terms of their spatial representation. So here's one day. You can see precipitation here across much of the Northwest. This is kind of showing you cloud cover across sort of eastern Idaho, extending up into central Montana. If we move forward a day, we can see that weather system moves through, precipitation moves southward and eastward, and again move forward another day. And we get these sort of fields that come out, and they're realistic fields that we can then use to actually drive other models, such as the hydrologic models that Sridhar mentioned. So what can we actually take home from some of these projections? There's quite a bit of information. In fact, there's several terabytes of information that I deal with. But I thought I'd make a few plots here that could be of interest to the group. And one thing is that we do see an increase in precipitation during the cool season. These models are predicting that. But they're also predicting an increase in temperature. And by and large, that increase in temperature wins out when we're thinking about the overall changes to snowfall. The exceptions being possibly in the higher elevations of central Idaho or in the greater Yellowstone ecosystem. This graph here is again showing us our change in projected water year snowfall for that mid-21st century versus historical conditions. This is a percent change from normal, so 100% means no change. 30% means a 70% decrease in snowfall amounts. And there are some areas here that are white, and those are areas that don't receive more than an inch of liquid snowfall per year. But what you can see here for RCP 4.5 and 8.5, you see a lot of decreases, and these decreases are fairly pronounced. You can probably focus on an area that interests you, and you're going to see decreases somewhere between probably 20 and 30% in terms of water year snowfall amounts. The decreases are quite a bit more pronounced in lower elevations. If you look at sort of the panhandle of Idaho, where much of the topography is below 5,000 feet, closer to the freezing level, those areas are much more vulnerable to this sort of a warming. So that's the overall changes in snowfall. But what also is relevant is the odds of getting an extremely low snowfall year. Those low snowfall years that might have economic ramifications for the ski resorts, water concerns for a variety of users, and also low snowfall years may also be linked to years of increased wildfire potential. And when we look at these models, we can actually get an estimate of how often these historically low snowfall years may occur in the future. And by historically low, I'm talking about sort of, you know, the sort of 1 in 10 year low snowfall amount. And what we end up seeing from these models is that what used to be a 1 in 10 year low snowfall amount could be occurring every 3 years or every 6 years under these future conditions by mid-21st century. So that's certainly an important take-home message.
This is going to make me cry.
Yeah. Well, there are going to be still good snow years, but more and more often we're going to be looking for these low snowfall years. One thing that actually is relevant is that in some cases there may actually be more snow, but it's going to be sort of closer towards the center of winter. So most likely the shoulder seasons are going to see the hardest hits. You know, the sort of the times of the year when, you know, snow is somewhat marginal today. Those ones are going to see some serious hits. Okay, and then one more thing here, if we sort of consider the other side of the coin, instead of thinking about snowfall, we can think about the moisture deficits. And moisture deficits are basically looking at the sort of potential evapotranspiration minus the available resources in soils, in soil moisture. And under future projections, what we end up seeing are, again, increases in moisture deficit, drier conditions, warmer conditions, leading to more evaporation. Also, by having our snowpack melt off earlier, that leaves much of the sort of higher elevations in a more vulnerable state, whereby currently that snowpack can melt and provide moisture deeper into the summer months. When we lose that snowpack, we could see much higher sort of moisture deficits. But overall here we're talking about an additional 5 centimeters or so of moisture, and that moisture is going to have to be coming from, if you're an irrigator, that's going to have to be coming from irrigation from whatever water resources are available. So I'll conclude here by just summarizing the importance again of climate in defining much of the resources and the culture that we know of in the western United States and certainly in Idaho. These climate models are models, and they're not necessarily meant to represent an accurate forecast, but they're represented to provide us with guidance on what the future might look like and how we might be able to adapt to it. They do a pretty good job at simulating historical climate and also the basic climatology of the region. And again, we talked about the regional warming of about somewhere between 2 and 7 degrees Celsius by the mid-21st century. This increase in precipitation, primarily in the cool months, but due to that warming, we should expect to see far less precipitation as snow, and that leads to a number of cascading impacts involving water availability and also the increased occurrence of these poor snow years. So with that, I think I'll conclude and open it up for questions that people may have.
This is Roger Furman, Idaho Power. In your summary here, you have slight increase in precipitation, Florida, and snow. Mm-hmm. And that's a common theme that we see in climate change results. But my personal observation is, it just seems to me like I'm seeing less precipitation overall. Mm-hmm. And I'm wondering if we've got that right.
Yeah, so that's a good question. I would say that we have far less certainty with respect to precipitation than we do to temperature. if you look at the models of precipitation, the projected changes, a lot of them are sort of overlapping with a zero change. There are more models than not that are predicting an increase, but the increases are marginal. And if we look at sort of climate of the past, say, 50 years, there's not really any obvious signal of increases in precipitation or maybe even decreases in precipitation. It really depends on where you are. And also it seems to be a factor of other variables like El Nino and the Pacific Decadal Oscillation. So in terms of a planning decision, I would say that it'd be a much wiser decision to sort of use that temperature information than the precipitation information.
Hey John, this is Sridhar from Boise.
Mm-hmm.
I have a quick question on the ET increase that you talked about with temperature. I mean, it's obvious that when temperature increases, ET might increase.
Mm-hmm.
But there are some, these climate models, I think, I wasn't sure exactly about how they are coupled. Do they talk about the feedbacks or, some literature, I think, cites the masking effect of some local cooling, and because of that, ET might change or decrease, actually, not increase, as you would see, with respect to increase in temperature.
Mm-hmm.
So how do actually these models deal with this coupling process, land and atmospheric feedback process?
Yeah, I think they all do it in a different way. That's probably one of the sources of uncertainty from model to model. What I will say, at least for the western United States, is that if we look at variables such as relative humidity, we see that summertime relative humidity in the western United States is expected to decrease. And also solar radiation is expected to increase. And that sort of corresponds with when you have decreasing precipitation in a region in the summertime. Usually, especially in the Northwest, you either have the storm track moving north or you have sort of monsoonal activity not making its way up. And that's sort of those variables by themselves, with an increase in solar radiation and a decrease in relative humidity, that's going to drive your increase in potentially evapotranspiration. I don't think that the models are doing the best job with sort of coupling land surface schemes and things like agriculture, irrigation into the large scale features of the models.
Okay, thanks.
Hey John, this is John Stevenson. I'm kind of going through and I'm trying to think about potential good news. I guess maybe one of the questions is, will the models, will they be able to tell us anything about changes in growing season?
Yeah, that's certainly a good. I mean, so I've lived in Moscow for 4 years now, and I've struggled to grow tomatoes in 3 of those years. And one thing that we have looked at is the length of the freeze-free season in these models. And for certain energy-limited areas, this is potentially quite good news. For example, one could look in different areas and one could see an increase in the length of the growing season by 1 to 2 months by mid-21st century. So again, that's sort of an increase in the potential growing season. Given that you have enough water, there could be significant agricultural benefits. And I know that there have been some studies done looking at the effects of climate change on dryland wheat farming up in sort of the Palouse region. And what they end up seeing is that warming conditions allow for the wheat to germinate faster during a time of the year when moisture is available. And that, along with the increase in carbon dioxide, that helps sort of photosynthetic rate, and it helps actually to increase crop yields.
So that's kind of like...
So I would expect that climate change is going to have its winners and losers.
Sure. So that was probably something on the early part of the growing season, that spring, there's still soil moisture and... Exactly.
Yeah. So crops that can take advantage of warmer temperatures early in the year, especially if it's a crop that requires early moisture. Those are going to be the winners.